Okay, so thank you for the introduction and hello everyone. So in this talk, I will introduce our work, performance and protection in the ZoFS user space NVM file system. I'm Min Kai from IPAS Shanghai Jiao Tong University, and the work is finished together with Heng, Jifei, Wen Chao, and our advisor Haibo. So non-volatile memory is coming with near DRAM performance, durable data stores, and the ability to be accessed by simple load and store instructions. So as NVM is changing the storage hierarchy, there are several file systems designed for NVM in recent years. Some of these file systems are implemented as part of the kernel and provide file system services via system calls, while some others, although requires kernel support, handle most of the file system logics in a formal user space library, and we call them user space NVM file systems. User space NVM file systems have several benefits. They are easier to develop, port, and maintain. They are flexible and can be customized to application demands. And most importantly, since NVM can be accessed by load and store instructions in user space file systems can directly manage NVM without going through the kernel, which makes them high performance. However, not all updates can directly finish in user space in existing user space NVM file systems. Updates, especially updates to metadata, are performed by trusted components instead of the user space file system library. For example, in Array, metadata updates are sent via inter-procedural calls and handled by the trusted file system service, while in Strata, all updates are logged in user space and processed by the kernel file system. These indirect updates in existing user space NVM file systems protect the metadata to ensure file system integrity and enforce access controls. However, they prevent the high performance of NVM from being fully exploited. For example, when two processes create a file in a shared directory, the latency of Strata is increased by 67 times compared to the latency when there's only one process creating files. The performance is even worse than the NVM file system implemented in the kernel. So in this work, our goal is to avoid indirect updates to fully exploit NVM performance in user space. Given that the indirect updates in user space NVM file system protect metadata but limit the file system performance, we strive to directly manage both NVM data and metadata in user space libraries while retaining the protection. To achieve this, we propose a cover abstraction that can separate NVM protection from management, and then let the kernel part to protect coffers via hardware paging, so that the user space libraries can manage all the in-coffer structures, including both file data and metadata. As a result, our system outperforms existing file systems by up to 82% and exploits full NVM bandwidth in some of the scenarios. So next, I will first introduce the cover abstraction and then introduce how we retain the protection using coffers. And finally, we present our evaluation and conclude. Our cover abstraction comes from the sense that applications tend to store files with the same permissions, and the permissions are rarely changed. Here is a survey on database and web server data files, which shows that most files have the same owner and permission. And according to our traces, this owner and permission are seldom changed during the application execution. This result inspires us to think that we can group files with the same owner and permission, and then map their data and metadata together to user space, and let the user space libraries manage this data and metadata directly in user space. So we propose a new abstraction called coffer. As we know, a file system is usually organized as a tree of files. We then group connected files with the same permission together to form a coffer. If a file has the same owner and permission as its parent, then it can be put in the same coffer as its parents. As a result, the file system tree becomes a tree of coffers, and each coffer contains a single file or a single directory, or a directory with some of its descendant files. Actually, a coffer is more than a group of files. It is a collection of NVM pages that have the same owner and permission. User space NVM file system libraries store file data and metadata on these pages. And each coffer has its own local space management to keep track of the free pages in the coffer. Each cover also has a root page that contains cover metadata, such as its path and permission. Cover enables us to separate NVM protection and management. With Cover, the kernel part of our system, called kernel FS, organizes the whole file system in a cover granularity. It protects the cover metadata and manages the global free space. And the user part of our system, which is called FS libraries, can contain multiple user space file system libraries called microfile systems. Each microfile system can define a different cover implementation, including different data and metadata structures and different approaches to managing local free space. We have also defined several cover APIs, and the microfile systems can call these cover APIs to request cover-level operations from the kernel. For example, to create a cover, map a cover to the user space, and split a cover, and so on. Next, I will introduce how we provide protection and isolation after using covers. Our system leverages hardware paging to provide strong protection and isolation. For each cover map request, the kernel FS first checks the owner and permission of the cover. If the current application has the permission, kernel FS maps the cover to the process page table as read-only or read-write accordingly. As a result, applications can access the cover only if they have the permission. Besides hardware paging, our system also leverages memory protection keys to further enforce protection. Memory protection keys is a new hardware feature that supplements paging. It allows the kernel to separate VM pages of a process into different regions. A user space write can control its own access to these different regions by updating a non-privileged register called PKRU. And any access violating the MPK access permission will trigger segmentation faults. In our system, when kernel FS maps a cover to the process, it ensures that different covers are mapped to different MPK regions for the process. As a result, applications writes can control its own access to each mapped cover efficiently by updating the PKRU register. With hardware paging and memory protection keys, kernel FS and the file system libraries can cooperate to solve several challenges with regard to protection, including stray writes, malicious manipulations, and phase sharing. As we know, applications may have bugs, and these bugs may cause stray writes and corrupt metadata in mapped covers. To prevent stray writes, we adopt an approach similar to the write window proposed in PMFS. To be more specific, all MPK regions are initialized as non-accessible in the PKRU register. When a microfile system wants to modify a cover, it first updates the PKRU register to enable its access to the cover. Then, it can update the data and metadata stored in the cover without triggering segmentation faults. When a microfile system finishes its modification, it should disable the access to the cover by updating the PKRU register again. Since the application code runs with all cover regions non-accessible, even if there are stray writes in the application code, the writes to the mapped cover will cause segmentation faults instead of destroying the cover structure. Besides bugs, an application can also be malicious or compromised and then try to manipulate a shared cover to attack others. There are 3 different cases that can happen, and due to time limits, we only introduce one case here, and please refer to the paper for the rest of cases. In this case, the attacker modifies a pointer to point to another cover. For example, there are 2 processes, the attacker and the victim. Both of them can access a shared cover, but only the victim can access the private cover. Since the attacker can directly modify metadata in the shared cover, it can modify a pointer in the shared cover to point to the private cover. Now, when the victim accesses the shared cover and follows the manipulated pointer, it will be led to the private cover. This will cause security issues such as data leaks. To prevent this, the file system libraries should ensure that at any time, at most one cover is accessible for each thread. In this way, when the victim is accessing the shared cover, only the shared cover is accessible as specified in the PKIO register. And when there's an unexpected pointer from to the private cover, the access would cause segmentation faults, preventing the victim from leaking secure data. And another concern is that an error in the file system libraries can trigger segmentation faults and thus terminate the whole process, which is unacceptable. Our approach to solve the challenge is to hook the segmentation fault handler and redirect the execution to the beginning of the user space file system operations. As a result, segmentation faults in the file system libraries are hooked and reported to the applications as file system error codes. With covers and the protection techniques, we implement an example user space NVM file system library called ZoFS. In ZoFS, we use adaptive two-level hash tables to store directory entries in a directory. We use simple direct and indirect blocks to store a regular file. And we also use list per thread allocators to manage local free space in a cover. Next is the evaluation part. So in the evaluation, we want to answer the following questions. First, can ZoFS scale and fully exploit NVM performance in user space? Second, how much performance benefit comes from the direct updates in user space? And third, how does ZoFS perform in synthetic workloads and real-world applications? We evaluate using Intel CPUs and the Intel Optane DC persistent memory modules. Our experiments are conducted on a single NUMA node with hyper-threading disabled. We compare ZoFS with 4 existing NVM file systems using serial benchmarks. Here is the result of FSMark. On the left side shows the throughput of creating files in a directory. On the right side shows the throughput of overwriting 4 kilobytes of the file data. In both cases, ZoFS scales well and outperforms other file systems for different concurrency levels. It's worth mentioning that for the data overwrites, ZoFS reaches the maximum NVM write bandwidth of our platform. To further show the benefits of direct updates, we add an implementation called ZoFS kwrite, which implements the write function in the kernel and invoked via system calls. As we can see from the figure, although ZoFS kwrite performs similarly with existing file systems, the user space direct updates in the ZoFS brings about 33% throughput improvement. We also reevaluate the previously mentioned scenario where 1 or 2 processes creating files in a shared directory. ZoFS presents the lowest latency in both cases thanks to the user space metadata updates. For the real-world applications, we run LevelDB's dbbench benchmark for LevelDB, and we run TPCC on SQLite. As the figure shows, ZoFS reduces the latency of all LevelDB test cases, and the largest latency reduction is 82%. And for the TPCC on SQLite, ZoFS achieves the best throughput and outperforms other file systems by up to 31%. To conclude, non-volatile memory is fast, persistent, and better addressable. However, existing user space NVM file systems have no direct control over metadata in user space and needs indirect updates, which leaves NVM performance underexploited. In this work, we propose covers which can separate NVM protection from management so that the user space file system libraries can directly manage both data and metadata of the NVM resources while embracing protection. Our example microfile system, ZoFS, built on covers, present better performance than existing NVM file systems in both benchmarks and applications. So this concludes my talk, and I'd like to take questions. Thank you.
Hi, this is Keith Smith from NetApp. So for fun idea, I really enjoyed the paper.
Thank you.
I know they're rare operations, but how do you handle change mode, change permissions that would, so a file no longer has the same permissions as its coffer?
In our cover APIs, the change mode or change on operations are handled by the kernel. So when there is a change mode operation, the user space file system libraries need to send actually a IO control system call to the kernel part, and the kernel part will maybe split a coffer into two, and to solve the permission changes.
So can a malicious user space library fail to do that and then keep a file in its coffer even though the permission is no longer correct?
When you want to change the permission, your permission is also checked by the kernel.
I'll talk to you offline.
Yeah.
Okay. Thank you.
Hi, Edward from Cornell, and I had a similar security kind of question, because you said that to enforce permissions within a coffer, you have the user space library set those special registers. So what if you have a process that loads a coffer that's shared with some other processes, and it's malicious, and they patch that user space library to not bother setting and checking those permissions so that they can read another user's files that are in that shared coffer? Is that a potential exploit because it's up to that user space library to enforce those permissions?
Sorry, I think I'm not totally get you. I'm not get your question completely, but since all files stored in a coffer have the same permission, so.
Well, you said that there were some coffers that were shared, like that root of the file system coffer.
Yeah. File system, yes.
And so that contains some things that should be read-only, but are shared between different users.
Okay.
What if a user just writes anyway because they don't use the user space library's permission checking?
Okay, so if a process can only read a file or read a file, the coffer is only mapped to the user space as read-only. This is guaranteed by the page table.
Okay.
Okay, thank you.
So Ethan Miller, UC Santa Cruz. You said that a coffer is all files with the same permissions.
Yes.
So what happens when you've got, let's say, a shared index and data that's particular to me or particular to Keith, and I want to be able to copy data between the two? Do I have to keep mapping in one coffer and then mapping in the other coffer, mapping in one, mapping in the other? Because, you know, one file that I'm accessing is just mine. The other one is shared between me and Keith.
So if you want to share a file to others.
No, just parts of a file. In other words, I'm saying I've got a file and I want to copy some stuff from it, but not all of it. What's that? Right, I'm worried about thrashing coffers, basically.
I'm not sure. In existing traditional file system, can you share only part of the files, part of a file to others?
No, I just read from one right to the other, which is pretty quick.
Yeah, you can read from one and write to the
let's
other.
take the question offline.
Okay.
So let's take the last one really quick.
Ian Neal, Michigan. So what persistence guarantees are you actually providing in the user space library that you evaluated?
You mean the crash consistency guarantee?
Yeah, because like for example, Strata actually provides like full data consistency for all of its writes.
Actually, the crash consistency can be implemented. The crash consistency implementation can vary from different user space file system libraries. And in our ZoFS, we just synchronously persist all the write to the file system, and we use some. As you know, each file system operation can be become a single atomic operation because, for example, when you create a file, you write everything else, and then finally you fill up the directory entry. So this is, I think this is similar to EST2.
All right, so let's take it offline for the next speaker. So let's thank the speaker again.